We can also measure the panel output. Most small solar panels have an output of 2 volts, some go up to 3. Ideal in range for using the solar panel as a sensor, because the hub can measure voltages up to 3,3 volts. We can measure volt by using the BB5, the BB6 or the BB7 port. Pay attention on the polarity and always check first with the voltmeter if the voltage isn't higher than 3,3 volts. If it's greater than 3,3, don't attach the source on the BB port. You can damage the hub. On screen, there is a very simple program. We connect a voltage source to the BB5 pin. There is a loop that 200 times reads this voltage. The sensor value, the raw data, is printed on screen. And there is a wait period of ½ a second between the measurements. So in total, the program measures 100 seconds. Added some extra time to execute the code, we have an experiment that lasts about 2 minutes. In these 2 minutes, we can see on screen what the voltage of the input source was. By using this method, I've mentioned it earlier, we receive raw data. It's the value of the analog to digital converter that is inside of the hub. This is represented on the screen. We know that these converters use 14 bits. 14 bits combinations of ones and zeros. If we have 14 zeros, the value is 0. This we have when we attach 0 volts. If we have 14 ones, the value is 16,383. That's 1 less than 2 to the power of 2 to the power of 14, excuse me. This we have by 3.3 volts. So if we apply some math, we can conclude that the measured voltage is the provided sensor data divided by 16,383 and multiply it by 3.3 volts. By adding this calculation after the wait 0.5 seconds instruction, we can display, besides the raw data, the voltage on the second row of the screen. As a voltage source, you can use the solar panel, but there are also many other voltage sources that can be used. You can use the output of a windmill, a battery, a rechargeable battery. You can let students conclude that there is a difference in voltage between an AA battery and an AA rechargeable battery. You can also use a battery pack, a transformer, a solar cell, etc., etc. Every device that generates voltage. But to keep it safe with children, do not exceed battery and voltage generator devices that exceed 24 volts. 24 volts is considered the threshold for safe tension. For the hub is 3.3 volts safe. So for the hub, do not exceed 3,3 volts. If your device exceeds the 3.3 volts, you can use the following solution. That's a voltage divider. A voltage divider is simple 2 resistors. The resistor R1 and the resistor R2 divides the input voltage between them. How much every resistor gets the voltage is a proportional function to the resistor value. For calculating BB5 voltage, you need to know the input voltage. You can measure it by a voltmeter and multiply this with the ratio of R2 on the sum of R1 and R2. To be sure, first create your voltage divider and then measure the output voltage of the voltage divider with a voltmeter. If that output is less than 3,3 volt, you're safe to attach it to the BB port. The students shall find it very nice to have a voltage meter made by themselves, but it's much nicer if you have also a visual representation. This visual representation can also be a research project for the students about light and colors. We have on the hub an RGB light already internally, so it's easy to use. There is also an RGB array that's sold separately by TI. What do we want? We want, if there is no electrical output, that there is a red light on. If there is a maximal output, we want the green light. And in between, we want yellow. You can make this behavior by a simple program, but it's much nicer if there is transitions between red, yellow and green. If we do some research, we can conclude that for red, red is on and green is off. When you increase the amount of green, the light goes from red over the color of orange to yellow. If both lights are on and you decrease the amount of red light, you go from yellow over light green to dark green. So take this into account with some mathematical concept. The mathematical concept is that the maximum value is 16,384. Nice in the half of that is 8,192. When over the half of the maximum number, green needs to be on and red needs to decrease from on to off. When under this value, red needs to be on and green needs to increase from 0 to 255. For doing that, it's quite easy. If less than the half of the maximum, red is also always on. If above, green is also on. For red and green to increase and decrease, we need to take some formulas into account. Because between 0 and 8,192, green needs to be from 0 to 255, we need to divide the data, the raw data, by 32 to have this effect. For red, it's a little bit more complex. From 8,192 to 16,384, red needs to decrease from 255 to 0. For doing that, we need to subtract from 255 the raw data minus 8,192 and divide that by 32. If we take this into consideration and translate it into a program, we have the following program that students can use to simulate the behavior without attaching a voltage source. So the raw data is asked to be typed in a value between 0 and 16,383. You see that there is an if statement if the data is smaller than 8,192 and else. Set color red on 255 and with else set color green on 255. Calculate the values we discussed earlier, and by using int we get a round number. Then we display it that red is on and that green has this value, and you see on the RGB LED the different colors. When I run the energy monitor program, the programming asks the data. When I fill in 0, the LED turns red because red is on and green is 0. With 2000, it's light red because green is a little bit on, 62 of 255. By 4000, it's light orange because green is a half on, 125 of 255, and red is still on. By 8000, red is on and green is on, so I have yellow. 10,000, The yellow turns a little bit greenish, 12,000. A light green color, 14,000. Darker green and 16,000. Very dark green, almost the maximum because red is 10, 11 of 255.